Hello and welcome to OpenCL GPU image filtering. Today we'll be taking a look at the Laplacian kernel, which is an edge detection filter. We'll go through this brief agenda quickly, and I'll begin first with the overview of the image processing pipeline. We first begin with our input image, which is then passed to a color space conversion operation. We perform some pre-processing to enable real-time performance by downsampling the input image, and that downsampled image is then passed to our 2D convolution filter, which detects the edges. We then upsample using a 6-tap interpolation filter, and again apply color space conversion to return the original input image format as the output image. We now turn our attention to the host code. Most of the classes discussed here are pure virtual classes. The image2D class and the image stream class are used in conjunction to grab images from a file stream. However, they could be used to grab images from any type of device capable of providing 2D images. The filter2D class is used to generate our convolution filters. The compute-util class is used to communicate with our compute device, in this case the GPU. Here we have a compute-util OpenCL implementation, showing a helper class as well as the derived compute-util OpenCL class. Next up are display windows. This enables us to show the input image and filtered outputs to the user on the screen. We also provide timing event objects. Used with the getPerf timer, we can provide timing statistics for our host code as well. The timing event stats class is used to provide first and second order statistics on our timing events. Lastly, we have our run task functions. These functions can be used to design our filtering operation, and we provide many parameters by which to control the output of the filtering operation. Now we provide a live code walkthrough. Here we have the option to set parameters, and we enter our run task, which we initialize our stream object, our perf timers, our filter, and load our kernel program. Stepping into the apply filter operation, we see this is our cascade of OpenCL kernels. First up is our convert YUV to RGB. We'll just step through this briefly. We create the OpenCL buffers, and after that's successfully run, we can gather some profiling info, just to show you how they enter into our timing class. Next, we perform some downsampling and are ready to run our convolution filter. Again, we set our OpenCL buffer objects, set the kernel arguments, in-queue our kernel to the device, wait for it to complete, and then unmap the appropriate memory objects so that they can now be consumed by the host application once more. And we are done. That is one complete iteration of our convolution filter. The rest just shows how we gather some timing information for our final statistics. We now discuss the Laplacian filter. The filter2D Laplacian is the implementation of the filter2D class that allows us to generate Laplacian filters. From the call make disk, we are able to generate the appropriate 2D Laplacian coefficients with the appropriate ring of zeros around the filter coefficients. It's a set of negative ones with a positive center. We now turn our attention to our OpenCL kernels. We start by providing two kernels to provide color space conversion, one going from YEV to RGB and the other from RGB to YEV. This enables us to perform all of our convolution processing in the RGB space. We also have a downsample kernel and an upsample kernel. The downsample kernel is a simple decimate downsampling routine. The upsample provides a 6-tap interpolation filter in order to provide a better quality output for the upsampling by 2. And finally, we have our convolution filter. This is a partially unrolled convolution filter that enables us to operate on 4 pixels at a time for each iteration. Any remaining pixels, because of the filter width, are processed at the end of the loop. Lastly, we also experimented with some separable filters, but these are not applicable to the Laplacian case, but for completeness, they were performed anyway. And last but not least, we take a brief look at the type of outputs we report. In the top set of data results, we show the time in milliseconds for each of the OpenCL kernels for each frame processed. We then show the mean and standard deviation, as well as the throughput in megapixels for all of our kernels. Thank you for watching, and hope you enjoyed.